So this is my lab report for Lab 4 Oscillations. To introduce this lab, the purpose of this lab was to compare a spring mass's oscillations, so its horizontal and its vertical movement that we saw in a video provided to us, to a computational glow script model that we coded in Python. And that model, I decided to calculate the potential energies and have the system with all of the forces in it. Some principles to note for this lab: the potential gravity and energy is equal to the mass times the acceleration due to gravity times the change in the vertical distance. Then the the potential spring energy, if you integrate the original spring force equation, you will get 1/2 times the k constant times the stretch squared. And then the kinetic energy is similar. It's 1/2 times the mass times the velocity squared. And for the purpose of this lab, we have the total energy equal to these two combined potential energies plus the kinetic energy. Another equation I wanted to note for this lab was the oscillation period formula, which has the time of one oscillation equals 2 pi times the square root of mass over the constant for the spring. In a preview of this lab, this is what my glow script little drawing looked like as it went back and forth with the spring mass. So this was the tracker video. When I put this video, we were provided into tracker. These were my clip settings for the time. Over here, I have highlighted in blue and circled in red the X and Y positions that I tracked at each of these time periods. And I put the X and Y positions into a CSV file because that's important for later when in the glow script model I actually compare these data points to the data points that the model creates for us. So these are the initial conditions for my code. So the ball mass we were given is 0.4. Sorry, the spring mass. So this ball, the spring position. So all I did was see where my cursor was, and it ended up being here at the initial negative 0.118, negative 0.623 meters, and then the initial velocity was equal to 0 because it was dropped from the guy's hand. One of the important things here is the spring constant K. Finding K, this oscillation period formula is important. You manipulate it to find K. You may be asking, how do I have T? And the way I have T is I just observed, and I found the average time it took for to get to each peak here for Y, and I could have done it for X, and it was about 1.519 seconds. So plugging this all in, I got this number right here. Then finding L0 right here, the relaxed length. Instead of doing potential, I did the actual net force. So I set the spring force equal to the gravity force, and then solving for L0, I get 0.127 meters. And then down here, these are the three equations we talked about: kinetic, potential gravity, potential spring. And then right here, we have the total energy equal to the sum of those. Calculation loop for my code. So the video was 9.5 seconds long, so I did, it's less than that. Right here, we have Newton's second law, the momentum principle. So this is the velocity update formula, and then the position update formula. And then up here, to actually calculate these energy changes that we plot later, doing the same exact thing for these equations as I had in the introduction slide, except now these are final. So this is the final kinetic energy, final gravitational potential, and final spring force. And we add these all up to an E final, and then we subtract and get the change in E. So these are the graphs. So comparing these graphs, they are similar. They have similar oscillations. Obviously, the red is a little rougher. There's a few jagged edges because of tracking. And, there's here, even towards the end, you can see that it starts to get a little behind, and the Y doesn't go as high or low as the model predicts. And some sources of error for that. One of the biggest things is that just tracking on tracker, the cursor might not be 100% precise every time on my part. So that's an issue with the experiment. Also, with the model, there might be other possible forces that were acting on the experiment that we didn't account for, like air resistance, which means that the system might have had some contact with its surroundings, actually. Now, finally, to answer critical lab questions, is the energy principle satisfied? And yes, it is satisfied because the energy stays 0 the whole time, indicating that there was no work done on our system by its surroundings, which is what we wanted to happen. And then finally, comparing the X horizontal and the Y vertical period of oscillation, I say that they're about the same. The X is a little less consistent. It's like 1.5 something, 1.6, but I think it's close enough to say that these frequencies are roughly the same. And that's all.